I want to share some thoughts about where we stand with irrigation with non-conventional water sources these days. I'm doing this from a perspective of a irrigation scientist and irrigator in Israel and some of our more arid and hyper-arid regions. The background that you see on this cover slide is a place where I work with farmers, and we do agriculture, and some of the landscapes even look more like this. Not all of them, but what we're talking about is regions with low rainfall, high climate demand for water and crops, and scarce water resources. And we expect that this is going to become that these kind of landscapes and this kind of situation with having not enough water and the need for looking for alternative sources of water for irrigation aren't going to be unique to where I work. We're seeing more and more situations of drought and dryness and water issues around the world. And we predict that it's even going to be worse. And in the next 10, 20 years, many of the areas that we live in, where we work, and where horticulture is important, are going to have a problematic ratio of withdrawals to supply of fresh water. We, in spite of that, are able to, in these landscapes and these areas, successfully grow crops and have successful agriculture, including with fruit trees and vines. Some of the reasons that we understand for being able to succeed in dry range regions, and this connects with adaptation strategies for climate change down the line, have to do with things that aren't involved with water, choice of crop and how we crop, how we support our farmers, policy including water that enables pricing and quotas to be able to be efficient with water, and especially water technology and supply. So going towards very efficient use technologies for application of water, like drip irrigation and decision support for smart decisions for irrigation are important, and even more important are what we're talking about today, which is the establishment of reliable sources for irrigation. So these sources can be multiple different sources, anything that's non-competitive with municipal and industrial consumers. It tends to be low quality, but not always. And sometimes there's tricky aspects of these water sources that can include harvested rainwater. I won't talk about today. Recycled waters from various sources. I'm going to talk mostly about municipal waste, recycled municipal wastewater, groundwater high in salt, which will term brackish water, and today more and more desalinated water has become a non-conventional source of water for irrigation. Now, as we look at these, water quality comes into it. None of these have a certain quality that we're able to completely define, but the trends are that the fresh water, depending on its source, tends to be have some salts in it, but be low in nutrients and contaminants. Treated wastewater tends to be high in salts with some to high nutrients and contaminants. Brackish water, by definition, is high in salts, may have some other things coming with the water, and the desalinated water is low in just about everything. Now, we're concerned with the water. That's what we're looking for. As an example, when we have recycled municipal wastewater, we find all kinds of other things in the water as we're doing it. Now, if I color these with yellow, meaning there's potential positive aspects from what's in the water, and red, meaning potential negative aspects in the water, we see that for the most part, all these things that we find in the water are potentially problematic to us, and therefore we're concerned. We're concerned as we're turning to these water sources about human health risks, environmental risks, agricultural risks that range from the whole range of our agriculture, from the soil to the products that we're producing. So we have to be aware and we have to study these things, and we want to make sure we're safe and not sacrificing and sustainable. We're particularly interested in macronutrients, micronutrients. Now, nutrients, of course, can be valuable to crops, but if we don't want them or if they're too high of a levels, it can be detrimental. We're concerned about salts, and I'll talk about problematic salts more in detail. But boron deserves a little bit more attention because it's unique, both in treated wastewater because it can potentially come with detergents in our waste stream, and also in desalinated seawater because seawater has a fairly high concentration of boron, and it's almost the only mineral nutrient that comes with a molecule that's small enough to cross membranes of reverse osmosis desalination together with H2O. And therefore, boron isn't so much of a current concern in drinking water, so we don't hear about it a lot, but it can certainly be toxic in both of these cases with crops. And so we must be aware of it. And probably the solution for boron is to be aware and to use policy to just remove it at the source and not have to deal with it down the line. Anyway, I want to concentrate on salinity because as we see, the real variable here between these sources of water and within them is how much salt is in the water. And we in places I work, we're irrigating crops and successfully, but with salinities of the irrigation water that are pretty incredibly high. And more than half of the rest of the irrigation water in Israel is recycled wastewater, and it's lower salinity, but it's still high in salts. When I do a back of the envelope calculation and assume all of the salts in the water are sodium chloride, and then multiply how much water we're irrigating in a season by the concentration of those salts, we're putting tons of salts onto our fields together with the water as we're irrigating with these kinds of high salt water sources. So what happens as irrigators? How do we look at those salts and what does that mean to us? We as irrigators know that we're really looking to replace the transpiration, that's the productive water consumption, and the evaporation, that's inevitable but non-productive water consumption. And we don't want to have any other losses of water in order to be efficient and very good at irrigating. When there's salts in the water that come with, especially when the salts coming with the irrigation water, and when there's salts in the system at all, almost all the salts come with the water to the roots. They accumulate on the root surfaces. They're not, for the most part, not absorbed into the plant, and eventually some of them are taken up. But the big problems happen as the water comes in, the salts stay out, and the osmotic potential around the roots becomes so low that it becomes hard for plants to take up water at all. If this accumulation continues enough, then the plants can't take up water at all. Eventually, the osmotic effects of salinity become toxic, but first on the roots and on the root surfaces, and then inside the plants. For this reason, we can't allow this accumulation to go too high. And as irrigators, it's not enough for us anymore just to give evapotranspiration requirements in our water. We need to give more water in order to leach the salts out. This is especially true in dry areas where there's not rainfall that naturally will take care of this leaching for us. So in the arid and hyper-arid regions that I work in, we need to know how much we need to leach, and we need to irrigate more. Now, how do we determine how much to leach? So we have several research tools in order to do that. The first are experimental. We use weighing drainage lysimeters in order to pose water and solute balances and to isolate variables of interest like the salinity of the water and the amount of water we're giving, the amount of leaching we're giving. And here we see examples for grapevines, for olives, for date palms, and for other horticultural crops that we can do these experiments and learn how much leaching we actually need to do. And of course, we also use modeling in order to be able to better take a look at the variables that are important in the mechanisms around the salt and the effects of the salt and the response of salinity, and be able to do to be able to look at each of these and look at sensitivity of them and really learn further. When we do this kind of work, we often get results like this. So what we see here is yield of sweet pepper fruit grown in a net house in a desert area with 2 irrigation water salinities, a low salinity and a higher salinity. Peppers are fairly sensitive to salt. And here what we see is we get a positive response to more water, seasonal water, until we reach evapotranspiration needs when the salinity is low. But we have a different kind of response curve where we have additional benefit. We have the effect of the salinity and additional benefit to additional water. What's happening here is that we're able to reach the same fruit yield, in this case for the peppers, at the price of twice as much irrigation water. Now, low quality irrigation water peppers here aren't inspiring more. All this extra water is going towards leaching salt. So let's talk a little bit about this water. So we needed to irrigate with more water. That water is leaching on the root zone, eventually getting to groundwater. Again, in dry area where there's not natural rainfall enough to leach salts out of the system altogether. We see data from a well that's downstream of this area where there's a lot of vegetables being grown in the desert. And we see over 25 years that the electrical conductivity or salinity of the water went up about 2.5 times. And what's really worrisome is that the nitrates in this groundwater went up 4 times over the same period. And those nitrates, the only source for them is the fertilizer coming from this vegetable production. So we're able to grow successfully in deserts using poor quality water. There's a big cost where the environmental cost seems to be huge, and this makes us question the sustainability of what we're doing over the long term. I want to then change direction a tiny bit here and talk about a little bit of the Israeli case, which is very unique and I think can teach us some lessons, because Israel is very early adapter and complete adapter of very efficient irrigation. So we in the 60s and 70s of the last century completely went to very efficient irrigation system, mostly drip irrigation, because of the value and the scarcity of our water. The next thing that happened over the next 2 decades of the last century, the last 2 decades of the last century, was the switch from fresh water to effluent and brackish water. And today this is even more extreme, with more than half of our irrigation water being not fresh water. This means we were introducing a lot more salts into our systems than we would have had before. And then the third thing that happened was around 2007 and up till about 2010-11, we very strongly switched to large-scale desalination to provide drinking water for our cities. And this meets agriculture in the quality of the recycled wastewater we're using for irrigation. So if in 2006, 65% of our water that we found, wastewater we found in reservoirs that was ready to be irrigated with, was higher than 250 milligrams per liter chloride. 10 years later, that was only 20%. 80% was much higher quality water than we had seen. So what happened over this time period? We took a look at a variety of things. I'm just going to show you a couple of national data coming from labs where farmers sent samples. So here we see citrus leaf samples that were tested for sodium over about 20 years. And we see a very worrisome trend of increasing amount of sodium in the diagnostic leaves over that time. These are not toxic levels, but the trend certainly is problematic. Now, what happened after about 2008, 2009? When we continue looking at this data, we have a complete reversal. So what we're seeing here is the increase of salinity due to the very efficient irrigation with low quality recycled wastewater. And then what happens when the desalination starts influencing the quality of that wastewater and making it better. So I think this is pretty interesting. The other thing that we found was we looked at sodium and chloride, in this case, sodium in edible crops that we found in the markets and on the farms. Here we're seeing them in relation to what we expect there to be in the same crops from a database from the USDA, FDA in the United States. And we see here that we're typically 2, 3, 4 times more sodium. Again, not healthy, not problematic, but the trend certainly is interesting and problematic. That just 5 years later, when we revisited this after the wastewater quality was better, we had reversed that trend as well, and only our perennial crops that are going to take a little bit more time were going to be under or the same as what we would expect in the United States. So I'm not going to spend a lot of time with the model. We have a model to predict plant response and environmental costs as a function of irrigation water salinity and content. The model wasn't being used very much until I managed to with a little bit of help, get it coupled with economics. It again, first of all, predicts water response as a function of salinity and amount. The model's built to be a planning tool. And no one was using it until we coupled it with economics. But by doing that and putting water prices and putting the then economic results of various amounts of water, salinities of water, crops, soils, weather, etc., we're able to get profit response curves. And these are very useful to decision makers, to farmers, to planners. Enabling them to look at sensitivity, not only of how much water they should expect to use as a function of salinity of the water for individual crops where they are growing them, but also how much they should be willing to spend when they for water if they're willing or if they have a chance to do so to get better water. So one of the things we were able to do with this is an exercise asking the question of, can desalination of brackish water be feasible as an alternative to using water high in salts? And the conclusion here was the cost of desalination could be justified for high value salt sensitive crops in our case under current economic realities. Which is a little bit surprising. A few more words about desalination and irrigation. We meet desalination both incidentally as we desalinate for water security, but more strongly as a source for treated wastewater. The cost of desalination, people usually ask, isn't it too expensive? Well, that depends how valuable your water is, and that depends how scarce it is. But it costs about half a US dollar per cubic meter to desalinate water. Brine disposal can be a big issue, especially when we're talking about inland brackish or wastewater desalination, not seawater, where we can put the salts back into the sea. We have to consider nutrients, boron that I mentioned, and often in dry areas, we're used to having sufficient calcium, magnesium, and sulfur in our water, which we no longer have when the water is really from desalinated sources. We kept potential, because the sodium is relatively high compared to calcium and magnesium, there's potential risk to soils due to high SAR from these waters. So just to summarize and finish up, non-conventional water sources for irrigation, we're talking mostly about recycled wastewater and brackish groundwater. This is a nice source of water that's not competitive with other consumers, and allows agriculture to have water, and it allows for waste disposals. There are certainly challenges in management, mostly about salts, also about crop nutrition, and about other contaminants that I didn't talk about today. When high in salts, these waters can inherently aren't sustainable in regions where we need them the most, the driest regions. Desalination is turning out to be a maybe surprisingly interesting driver for potential sustainable arid region irrigated agriculture down the line. I think we should spend more attention and time talking about desalinated water. I have a lot of co-authors and a lot of papers, both with the kind of storytelling that I'm giving today, and going and also going a little deeper into mechanisms and the science behind what I'm talking about. And with that, I'd like to finish and thank you.